So, starting from where we stopped last week, so we tried to look at Kaggle, a very popular data science website where you have a lot of competitions, most especially data set that have sizable number of samples. So last week we looked into example from the medical field where we actually considered hypertension data set that is using basic features. We can actually detect earlier on if someone is hypertensive or not. And we gave justification to why this kind of work is very, very important. Because majorly because the main method of determining if someone is hypertensive is to measure the blood pressure, which is very subjective and also open to being affected by several situations. Either you have a lot of tasks ahead of you, you are so busy thinking about some stuffs, even drinking tea before you go for your measurement, and a host of many things that can affect the measurement. I would say it would be very great to have a machine learning system or model that can be able to just ask you a few questions and then it can predict if you are hypertensive or not. So it's a very interesting area for me personally and my team. We've been working on it and try to get more live data set to see if you can push up something that can benefit the people, humanity in general. So rather than letting people live with hypertension for years, getting their organs destroyed before they finally detected. So today we are going to look at another very interesting data set of here we have it here, absenteeism at work. So absenteeism at work. So in some area it may not be a big issue, but it's a very big issue when you look at the number of manpower that is often lost in the course of because due to absenteeism at work. So a company expecting their partner to visit and suddenly the main person involved is just got him or herself absent that day. That's a very big deal for that company. And also for that negative issue that will affect company by as a result of absenteeism. So absenteeism at work, a very common data set we are going to check it just out now. We can see that in reality, imagine that your manager just call you maybe late in the night previous day and telling you, hey, guy, please make sure that please tomorrow you try to be at work because we have important visitors. And meanwhile, you're already thinking that you are not going to go to work that day. So yeah, the system is possible. So the manager just need to run the machine learning model at his hand and then be able to say, who might actually be absent. And then we'll try to reach out to those workers to try to persuade them not to be absent. Yeah, technology has gotten to that level that you can know ahead of time that, okay, maybe this guy might be absent based on some of the attributes. So now let's look at it together and try to bring in the data set from Kaggle as the case may be. So you can see here, either you go straight to the search. See, whenever you need any data set, either you are needing for house price, we are going to hopefully have it like later. You just need to type whatever you want to search, absenteeism at work. You can see here, you are going to see, yeah, lot of stuff there. You can see the different ones there. You have to look at the one that is really related to the data set that you are looking at. And one thing here that is good about this site, which I strongly recommend to us, is you can see if people have worked in that area before. You can see some of their work. Some of them have uploaded their work here. Some of them you can have linked to their papers. See? So you can say anyone that work in this area, someone use clustering. So, but for now, so looking at it, you can see a lot of things you can check out if you are interested in such working in such projects. So to build a model that can be able to estimate the number of hours that somebody might be absent, or as the case may be. So, and originally this data actually came from UCI repository, which ILA gave to us. So we can also check it out. We check some in our previous lecture, we do look at UCI dataset repository. So it was brought in here to Kaggle by people from those areas. So for easy sharing, and you can see people even share their code, they share their models, and also for that. So we click the data set. We want to really see the data set and download it. So we can see here, there's going to be a little bit of description. If there's any code on it, you see the code, you did discussion about it, as the case may be. So this is explanation of the data set. So it's good to look at the data set. You want to see details of how the data set has been built or whatever is related to it. We can check out the discussion, as the case may be. You can see different explanation posted. Meanwhile, so let's look at the data set itself, which is our main goal. We want to get out the data set. You can see these are some of the details about the data set. You can see task ID. You see these are the other attributes: reason for absence, month of absence, day of the week that the person was absent, seasons, and also further questions. So let's just download the data now. So having successfully downloaded the data, then we can look into it. So we can also check out others, like you check the columns, what are the information in the columns. You might even want to use some of this basic information or visualization in your report writing. Now, so you check the compact form. So, and also for that stuff you can have. So the data is already in CSV. You can see CSV. So which is another good thing there. So you can check out authors, people that have worked in that area before, the citation, and also further information about the data set. You can see it's a very popular data set. I've already viewed 7,000 plus, 629 downloads, then contributors. So, and also further information. So now let's open the data, and then we check it together, and then see. Now, so this is the data set, open in Excel. It's already in CSV format. So you look at the attribute before you take it to the WEKA environment. This is very, very important. So this is the ID. This is reason. Can expand the reason for the absence, month of the year, season of the year. So transportation expense. So maybe this can affect somebody not coming to work. And maybe towards the end of the month, maybe has no more money to be able to make transportation to the office. So this can be used a lot to actually, the company can use to really see how to put intervention system that can prevent people from coming to work. So by maybe going to have different type of payment, pay them on maybe on weekly basis, their bonus, pay them special bonuses on weekly basis, especially if we find out that transportation issue is one of the things that we often have. Especially if the modeling revealed that transportation is one of the causes or strong causes of being absent from the office. So perhaps company might want to put up a system that can encourage staff to be paid maybe some special allowances on weekly basis, so that at least you have something apart from the monthly about the monthly take home. You have something to always make people to be kind of fluidity in terms of financial capability. So we have distance to the residence also. Maybe it could be also a point to note. Service time, age. Does age also play a role? Workload. Perhaps the workload also might be what is scaring people from coming to work. So it targets, so disciplinary failure. So the education, some of them are coded. When you have look at the description of the data set, all this will be made more clear. So social is a drinker, is a smoker, does keep a pet, what is the weight, what is the height, then what is body mass. Then finally, we have what we want to predict, which is absenteeism time in hours. That is how many hours this person is going to be absent from work. We have 0 there. If it means somebody is predicted to have 0 absent, it means he's not going to be absent. You see, he's not going to be absent. See, so having gotten the data, the first thing you have to look at, if you look at ID, this ID is not having anything to do with our model. You should not use ID for modeling. So, and then you have 2 options. Either you remove it from your data set before you upload it to WEKA, as we're going to demonstrate now, or you let it remain. However, after uploading it to WEKA, you must always remember to select it and remove it from WEKA. Why inside WEKA, before you model, you can remove attribute there. Okay, don't use this attribute for this modeling. However, the problem that could arise from that is sometimes people, once they upload data to WEKA, they forget to remove those attributes that are not relevant. If you know you want to keep the original data the way it is, I want to be able to know what is the ID of each of the participants, that's okay. However, you need to remember that in WEKA, you must uncheck. Because using ID to train your model and using ID as one of the features for training your model is just going to contribute negatively to your modeling, because ID has nothing to do with how somebody is going to perform. Yeah, it's just like his name or whatever his national ID or whatever you can use as ID. So this is just an identification number that could be used for someone or based on the way data actually has been collected. So, and then except when it will be used for other things, because in the ID you can notice some repetition, where some people maybe perhaps absent at different times, or as the case may be. So that's why we can kick out the ID. So leaving us with the remaining attribute. And then this is the target, which is already in the rightmost part of the CSV file. I suggested to Rob, we should always make sure that we place the target, which is the attribute to be predicted, let it be at the right side if you're using WEKA. Because once you upload it to WEKA, if it is not in the right side, then you need to specifically tell WEKA that this is my target. See, otherwise, WEKA will use the rightmost attribute as the target to be predicted, which means you'll be predicting wrong attribute. So that is why it's always good. You can remove this from it manually if you want. And then, but this one, it is already in the right side. Sometimes when you download the data, you can find out that the data is here. I mean, the target value could be here. Then it's advisable for you, if you want to use WEKA, just move it to the rightmost part here, so that you don't run into you just want to stop the risk of forgetting to declare the specific target you want to predict. So that is looking at the target. Now, something also very important or very interesting to note is this, is that we want to predict absenteeism number of hours, how many hours someone is going to be absent. See here, when you check it, you can see there's some 0. 0 means no absence. So in case I want to create, because sometimes you have a problem, even though the client send it to you as regression problem, I can make it to be multi-level predictive solution. Multi-level in the sense that I will first of all create another data set from this data. From this absenteeism in hour, I will create yes or no problem classification. That is, first of all, I want to predict if this person is going to be absent or not. That is yes or no. So it means 0 means no absence. Why anybody with number 1, 2, 3, or to any number is going to be absent. So in that case, we are going to have 0 to mean no absence. And then this one will become yes, this one will become yes, all the other numbers become yes, because those are people that are absent before. So because this is historical data. So all T0 become no, the negative class. So in which case, it means I will convert that data set into classification problem. So I first run a classification problem on this set by predicting, is it going to absent or not? That is stage one of my prediction. Then the next stage, I want to check if you are going to be absent, how many hours are you going to be absent? You see, because why we do this sometimes is usually very challenging when it comes to regression problem, especially if the range of the data set is a little bit huge or bigger, as we are going to see. So, and the number of, you can see the number of features is relatively high. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. That's 18 minus the ID, then plus the target. So, and the number of feature is number of samples. It's not really very high. We have only 741, which is it's good to start with. But considering the number of features, ideally we should be having 18 raised to power 10 feature, 10 samples. So the number of feature is relatively high, while the number of sample does not measure to that. But this is a very common problem with data set in machine learning. So bearing this in mind, when you run this kind of experiment, well, let's see what our data is going to say. So now I'm going to open the WEKA. Let's transfer now to WEKA environment. So you click your Explorer, and then on the Explorer pop up, then we can go ahead now and then try to open the data set. The first thing is to open the data set. So open the data sets. I think I have it. Yeah. No, sorry. Yeah, the data sets located, I think it was in my download folder. Should be in my download folder, I think, yeah. So you can see here, I can see data set here because I need to, it's looking for ARFF. People do make this mistake, so don't forget. You need to change it to CSV data file. Then you can see the data, you can see absenteeism at work, so you can load it to your system. Now it is loaded, ready for work. Now, so you can see here, these are the attributes after loading the data to WEKA environment. So the next thing is, we check it. If you see the number, the ID is still there. So we need to remove that ID from using WEKA, since we decided not to remove it manually from the Excel file. Even though I usually prefer to remove it manually there so that you don't forget to remove it. But forgetting to remove it means I'm going to be using the ID as one of the features for training my model, which of course might likely affect the result. So here you just select here. So you see remove button. You can remove it. It does not remove it from your data set in Excel file. It's going to remove it from the WEKA modeling environment now. Remove. So you have removed that. And you can always bring it back. You can just say undo. You can see here, undo. So what you have removed will come back. So, but since I want to do modeling now, so I need to remove it because I don't want it to be used. So now I'm having like 19 features, and then the 20th is the absenteeism. You can see here, which is this, can check the statistical distribution, the minimum, the maximum, and then the standard deviation. For sure, you can see the predictives. You can also check others. So, and then see how it goes. Now, having done that now, so we are ready to go. So let the data speak. So we choose classifier. So as usual, let's choose our friend. Since we are now dealing with, something to note now that this is a regression problem. So from the onset, we know we want to predict how many number of hours that somebody will be absent from work. So it's a regression problem. So we choose the classifier we want to use, or the algorithm. So let's use our friend. So IBK, our lazy classifier. Let's say percentage of 70 to 30. So because we are dealing with regression problem, we should be expecting to see correlation coefficient, root mean square error. We already described this earlier in our previous videos. When you are dealing with prediction of real numbers, then the quality measure you are going to use or the performance measure will be different from those of classification. So you click start here. You can see the k-nearest neighbor, I think is done. This is the correlation coefficient. See, very, very low, very poor. This is the correlation. That is the predicted value against the actual value. This is the correlation coefficient, is 0.0, very, very low. So the mean absolute error, root mean square error, 17.54. Usually correlation coefficient and root mean square error are very, very popular for regression problem solving. Of course, when you are solving a problem, you look at published paper in those areas, and then you pick up the performance measure they have used so that you also use them. If you feel they have missed out a very important performance measure, then you can add it to your own, but you can only compare your own based on what they have used. That's why it's always good to refer back to earlier work when you work with this kind of machine learning outcome. So this is the testing set, that is the 30%. We use 70% for training, 30% for testing. So, of course, this is, remember here, you can click here to optimize. We are using the default k-nearest neighbor, which is k is equal to 1. Let's see, maybe when we increase our k, we need to do optimization of the parameter. When we increase our k to 2, let's see, maybe there's going to be a difference in the performance. Can you see here? It's improving 0.2. You see? So let me keep doing that. Let me make it 3. That's the number of neighbor I want to use. It's 3 now. Start. See? 0.2 still. So let me use 4. Can see it goes down. You see, it indicated that it seemed I got the best at k is equal to 2. I still have another parameter optimization to optimize. If you remember, we need to optimize the distance measure. It's presently using Euclidean distance. Let us change it to shape distance and then see what we get. So here we run it again. It goes down. So you know how to do, this is called hyperparameter optimization. You need to check what are the hyperparameters that will work for the data set we have. And that is following the principle of let the data speak. So we already had videos on how to carry out hyperparameter tuning in WEKA. So we can check this out. Now, so we have selected this, so we can do the parameter optimization later and check. Another thing that you might want to check also, maybe the number of features. But before you go to this, it's good to try other algorithms, because last few weeks we discussed the idea that machine learning is not a dogma. And the idea is that there is no algorithm that is always good in all situations. No. And that's why we have let the data speak. If you remember last week in our presentation on hypertension data set, this same k-nearest neighbor achieved 100%, even without any hyperparameter, using default value of 1, k is equal to 1, and the default Euclidean distance. It achieved 100% accuracy. It means I want to predict someone is hypertensive or not using this algorithm, I get 100%. But now look at the same algorithm now. It's struggling to get even 20. The best now we could get is 25.9% correlation coefficient. And very high root mean square error. Of course, it's lesser than this. Initially, it was 17. So maybe with more optimization, we might be able to get it a little bit higher. but I don't see it getting so high as because it started a little bit lower. So now what you have to do is, since there's no algorithm that is always better, the fact that K-nearest neighbor was better last week on hypertension data set, it doesn't guarantee that it's going to be better on absenteeism data set. So we go for other classifier or other algorithms. So let's go for like maybe let's use our friend, let's use support vector regression, SVM, and see what we can get. So you see SVM again is starting, it's 28% in correlation coefficient, 0.28, that's take it to percentage, is going to be 28.11%. The root mean square error. So we have to do hyperparameter optimization also for support vector machine. So okay, here, the most important hyperparameter, as you know, the first thing is the kernel. You have to check your kernel. Which kernel is going to perform better for us? So we have to choose. Is it polynomial kernel? Is it normalized polynomial? Is it RBF kernel? We have to try different kernel. The most important hyperparameter in support vector machine is the kernel. So we first of all try to see, okay, can we get the best type of kernel, and then see run. Is it still not very big improvement? So we have to do the hyperparameter optimization. Okay, maybe I should see the next important hyperparameter after you play with these guys, different ones. So to see which one gives you the best is to go for C. C is going to be, maybe I change my C to like 100. It can be any number, any positive number, 0.5, 0.6, and can be as high as possible. So start. So AI here, you run it. Yeah. You can see here now that changing the C made a little impact. It's changed to 31% correlation coefficient. So I want to believe if we keep going with the optimization, increasing C, or as the case may be, let me try 1,000. See? So this is just random checking. So in your hyperparameter optimization, you have to really go to do it professionally. I mean, try all the possible options. And we already made videos on how to do hyperparameter optimization. You see, so sometimes you can do the grid search method to search for as many as possible, or as the case may be. You can see the more the C value, you can see it's taking longer time now. It's taking longer time, and that, let's see, may hope it's going to get something good, but that doesn't guarantee that it's going to get something really good. So just because the value is higher. So you do hyperparameter. We can also try to select other algorithms, see, that are there, what of our multi-layer perceptron. You see? So let's just wait a little bit. It's almost done. Time taken to build the model. It took 45 seconds. So hopefully it's doing the testing now. So hopefully it doesn't take more time. We see what we get. Then we can move to checking what's going to be the performance of multi-layer. So it's done. We can see even though it took so much time, still it came back with lower performance. The previous one was 31%. Now it's getting 30% correlation coefficient. So that's hyperparameter is very important. We play with the hyperparameters. Once we have done the hyperparameter for different algorithms, none of them is even getting 50% now. And we are aiming at 90-something%, if possible, 80-something%, depending on what people achieved earlier. We have to always look at the previous earlier work and see how far they were able to go in absenteeism prediction. So we can go for neural network, for example, multi-layer perceptron. Let us also tell us what can you see from this data set. So using the default, it seems you can see even support vector machine that used to be very powerful is getting 31% this is neural network is getting 21%. Of course, we need to do hyperparameter optimization also, but then we already described how to do that. So interested people in this kind of work can pick up these data and I really encourage us, pick up your own data that either you like this one, the hypertension data set, or any medical or any area that you are interested. Please explore, pick up your own data and try to see how you can demonstrate modeling. Now, we have seen that none of the 3 or 4 algorithms checked for now has been able to really get higher results. So suspect the data is a little bit somehow. Yeah. The hypertensive data, if you remember last week, it has almost 23,000 plus samples. That is very nice data. See? And the number of features is not up to this one. This one presently has 19 features. So we need to do feature selection so that we can say, okay, which feature is going to be better for us? You can do select attributes, choose the method to select the attributes as the case may be, and then choose the attribute selection. I want to use maybe correlation-based attribute selection, and I say start. You can see correlation attribute selection. We select what are the attributes that have better performances. It has ranked them now. You can see them. This is the one with the highest value. This is the correlation coefficient between the input and the output. You can see almost every attribute in this data set is having very low correlation with the target. So perhaps this is why getting very accurate result is getting challenging, because this is 0.14. Sometimes we have 0.9, 0.8. It means they're highly correlated. They're likely going to suggest better prediction. But notwithstanding, we can select the best 2. The best 2 is height, sun, or maybe the best 5. So you just go there and remove those that are very low, especially those negative, as the case may be, or those ones that are really, really very small. So we can remove them. We go back here, pre-process, remove some of the attributes that maybe are not showing, indicating that very low correlation. We can just remove them. See, you remove the attributes. Then you go back again, you run your model and see, maybe you are going to get better result. Wow. Can we see something? I just removed some attributes now. Now, neural network is getting 99% accuracy. Just imagine. So that is the power of feature selection. Now, let me try even the k nearest neighbor this time around, our lazy classifier. Let me see what it's going to get. Even k nearest neighbor is not left behind. Suddenly, it's getting 99.67%. It means there are so much attributes that makes it very difficult for the model to be able to generalize on the data set in an appropriate manner. So that's why we already cover feature selection, and we talked about the concept of cost of dimensionality. You see, the moment you have data sets that are very huge, you have features, many features, but the number of samples are reduced. You have to be very careful, because in this particular experiment, I can do, let me undo now. I want all this data set, all these features to come back, undo. Now I have my phone. 19 features for 741 samples is just too small. So when you reduce the number of features, and how do you reduce the feature? You try to do like correlation coefficient, very simple one. Those ones with very low correlation value, you can remove them from the data set, because it means they're not contributing enough to that data set. And we can see this is just initial removal. We can even still remove more, you see, so that we are left with those ones with very high correlation coefficient. And then we see that by removing even less than half of the features, we already got classifiers getting 99%. This is the same k nearest neighbor. It means if you have wrong feature in your data set, this could be a means for someone not to get the best possible result outcome. So that is demonstrating the outcome of using the absenteeism data set. And then to remind us once again, the procedure is in machine learning schematic diagram. It's a general principle. You start by having your data set, which we have gotten from Kaggle now. Get your data set. Now go to the algorithms environment, go to the modeling platform, which can be any platform you have, you like, you are comfortable with, MATLAB, WEKA, Python. It doesn't matter. It can be any platform. Then we select the algorithm, and then we check the performance measure. You can see we did that. We noticed that they were not performing on this absenteeism data set. Then we try to use other model. You can go back, use another model. Then we try a couple of other models, support vector machine, neural network. We found out that yet something is not working. They were not getting improvement. Then we go back. Sometimes we have to go back to the data. We do feature selection. We remove some features that we think and might not be contributing positively to the predictive solution. And we found out that by removing just few of the features, we're able to get 99% quickly, using even some of the simple algorithms like k-nearest neighbor. So which means there are some features that are there, they were just pulling back the work, they were not contributing. But by identifying those features, removing them, we were able to achieve excellent outcome. So this is, again, demonstrating that you can do it, everyone can do it. So get yourself to practice. Machine learning can be best learned by practice. Practice the little you've learned, get data set, upload it to the platform, then try to see the prediction you can get. If you're not getting something good, go for other algorithms, because no algorithm is better in all situations. Check out few other algorithms, and then if you are not getting better result, then maybe something's wrong with your data set. Do you need to normalize your data? Do you need to do feature selection? As a rule of thumb, once your feature set is much, like 19, and the number of samples is not very much, because ideally when you have 19 features, you are supposed to have like 19 raised to the power 10 samples, but the data set is not always available. So go back again to feature engineering, try to see how you can remove the features that are not contributing by using different feature selection method that we have described. So you can check up our earlier videos on how to do feature selection. You can see that in this data set, absenteeism prediction, it was the use of feature selection that made it possible for us to achieve from 25% up on 25% correlation coefficient, move to 99% accuracy by just doing feature selection. So this is how you do modeling from data sets taken from Kaggle. It could be from any other platform or any other data source. You can even make your own data set, and then to building your model in WEKA. So thank you very much. So that's what we are going to have for the week. Wish you all the best. So I'm going to take a couple of questions if there is. Thank you very much for listening.